Welcome to the deep dive. Today we're taking, well, a giant leap really, 40 light years away. We're looking at a planet that's, it's really shaking things up. Trappist 1b. For the longest time, everyone thought scorched rock, no atmosphere. Simple. But new findings, they're turning everything upside down. Okay, let's unpack this.
Right. And what's fascinating here is this goes straight to the heart of the search for life. You need an atmosphere. I mean, no air, no liquid water, probably no life as we know it. Trappist 1b, it's the closest planet to its star in this amazing system. 7 Earth-sized planets orbiting a little red dwarf star. 3 of them are even in the habitable zone, but this one, 1b, being so close, the assumption was just radiation-blasted wasteland, barren. Now, the James Webb Space Telescope, the JWST, it's suggesting maybe it does have an atmosphere, which is huge.
That is a huge twist. So, 40 light years, how do you even study an atmosphere from here? What's the method JWST is using?
It's actually a pretty ingenious technique. It's called the secondary eclipse method. So picture the planet going around its star, right? When it dips behind the star, from our viewpoint, its light vanishes for a bit. By measuring the total infrared light from the star and planet just before it disappears, and then just the star's light when the planet is hidden, well, the difference is the light coming just from the planet. It's incredibly sensitive work, like trying to figure out a fly's weight by weighing a truck with and without the fly. But JWST can do it. And they looked at specific infrared wavelengths, 12.8 and 15 micrometers. These aren't random. Different molecules, they absorb or emit light at very specific points, like fingerprints. 15 micrometers, that's a classic spot for carbon dioxide, CO2. 12.8 micrometers. That can tell us about different heat properties, maybe even emission from warmer layers higher up.
Okay, so they point at JWST, used this secondary eclipse thing. What did those first measurements, especially at 15 micrometers, tell them? What was the story back then?
Well, yeah, the 15 micrometer data, it created a bit of a puzzle. If Trappist 1b had a typical atmosphere with a good amount of CO2, you'd expect to see that CO2 absorbing light there. It would make the planet look dimmer at that specific wavelength. But they didn't see that dimming. The signal was brighter than expected if CO2 was doing its usual absorption thing. So that really pushed scientists towards the dark, bare rock idea. Just a world with no real atmosphere like our moon, soaking up starlight and just radiating heat back out. Kind of bleak, honestly.
Right, so bare rock seemed to fit that first piece of data. A bit disappointing, maybe, but science keeps going. What happened when they looked again but focused on that other wavelength, 12.8 micrometers? You said this is where things got weird.
Exactly. Here's where it gets really interesting. The 12.8 micrometer data just didn't match the bare rock story at all. Based on the 15 micrometer results and the bare rock idea, the planet shouldn't have been as bright as it was at 12.8 micrometers. It was too bright. So that simple picture, suddenly it didn't work. This contradiction opened the door to 2 really unexpected and frankly way more exciting possibilities.
Okay, scientific plot twist. Let's dig into the first one. A geologically active surface, but incredibly young. What does young mean for a planet billions of years old? And what could keep it so active?
Yeah, incredibly young here means the surface might only be like 1,000 years old on average.
Yeah.
Compare that to Earth. Our continents are billions of years old. Even, recent lava flows are ancient compared to this idea. 1,000 years is it's basically brand new geology. And what could cause that? Just constant, intense geological activity. Think massive volcanoes erupting nonstop, maybe even super fast plate tectonics constantly recycling the crust. The driver, probably immense tidal heating. Trappist 1b is so close to its star, plus it's getting gravitational nudges from its 6 sister planets. All that pulling and squeezing could keep its inside molten, fueling endless eruptions. It'd be less like Earth or Mars, and more like Jupiter's supervolcanic moon, Io, just this chaotic, fiery place.
Wow, okay. A volcanic dynamo constantly repaving itself. That's one possibility. But you said there was another, maybe even more mind-blowing one, something involving CO2 again, but in a totally different way.
Yeah.
How does that work, especially after the first measurements seemed to rule out CO2?
This is the really wild one. Possibility 2. Trappist 1b does have a CO2-rich atmosphere, but it's hazy and behaves, well, weirdly. Unlike anything in our solar system for a rocky planet. Remember, at 15 micrometers, we didn't see CO2 absorbing light like expected. But what if there's a thick haze high up? Think maybe like the hydrocarbon haze on Saturn's moon type, but different composition, obviously. This haze could absorb incoming starlight, heating up the upper atmosphere, making it hotter than the layers below. That's called a thermal inversion. Okay, so you've got the superheated upper layer. Now, the CO2 molecules up there, they're so energized they don't absorb light at 15 micrometers. Instead, they actually emit light, especially strongly around that 12.8 micrometer wavelength we measured. So the unexpected brightness isn't from the surface, it's from CO2 glowing high up because of this thermal inversion caused by the haze. It completely flips how we think CO2 behaves atmospherically. This kind of atmosphere would be unlike anything we've seen on rocky planets in our solar system.
So, volcanic chaos or an alien, hazy, glowing CO2 atmosphere, two completely different worlds potentially explaining the same light signals. That's dick complex. How do scientists even begin to figure out which one, if either, is correct? What are the next steps?
Yeah, it's a huge challenge. Space science is tricky. These atmospheres, if they exist, might be thin, their signals are faint, easily buried in noise, even for JWST. Plus, the star itself, Trappist-1, it's a red dwarf. They have massive flares, big star spots. All that activity can mess with the measurements, make the data noisy and harder to interpret cleanly. So what do? More observations. Lots more. There's actually a big commitment now. NASA just approved a program called Rocky Worlds. It's dedicating 500 hours of JWST time just to study the Trappist-1 system. That's a lot of telescope time. The plan is to map the planet's temperature as it orbits, look at the difference between its day side and night side, how heat moves around. That thermal map should, hopefully, give us the definitive clues needed to tell if there's an atmosphere, and maybe even start to figure out its structure. Is it bare rock? Is it the volcanic scenario? Or is it this hazy, inverted atmosphere?
Okay, so the investigation is very much ongoing. Stepping back, though, why should we care so much about this one specific distant planet? What's the bigger picture here? You called it a cosmic laboratory.
Exactly. TRAPPIST-1b is not just a planet. It's a cosmic laboratory. Because red dwarfs like TRAPPIST-1 are the most common stars out there, like 70% of the stars in the galaxy. Understanding how planets form and evolve around them is crucial. Can planets this close to their star hold onto an atmosphere? What kind of geology happens under such intense tidal forces? TRAPPIST-1b is giving us a unique window into these extreme processes. It's pushing the boundaries of our models for planet formation and atmospheric science. It helps us understand the sheer diversity of worlds the universe can create.
And connecting it back to that big question, the search for life. If 1b, the really hot close-in one, could have an atmosphere, what does that mean for its siblings further out, the ones in the habitable zone?
Ah, yes. If we connect this to the bigger picture, it's a massive clue. If TRAPPIST-1b managed to hold on to some kind of atmosphere, despite being blasted by its star, well, that significantly boosts the odds for the other planets in the system, especially those 3 in the habitable zone. It suggests atmospheres might be tougher, more resilient, maybe more common around red dwarfs than we thought. And if those planets in the habitable zone also have atmospheres, then you potentially have liquid water and, well, you have the potential for life. Suddenly, the TRAPPIST-1 system isn't just interesting, it's arguably one of the most promising places we know of to look for signs of life beyond Earth. This brings us one step closer to answering, are we alone in the universe? It really does.
So to sum it up, we're looking at TRAPPIST-1b and seeing maybe a volcanic dynamo constantly churning its surface, or this hazy CO2-rich world with a probably alien kind of atmosphere. Incredible.
Either possibility is pretty mind-bending, yeah.
It really highlights how these amazing scientific tools are bumping up against some of the universe's deepest mysteries. So what does this all mean? Is TRAPPIST-1b just a stepping stone, a really fascinating cosmic curiosity for scientists? Or could it be more? A hint that the conditions for life, or at least the atmospheric precursors, might be far more widespread than we ever imagined. Something to ponder. Thanks for joining us on this deep dive.